right. Hello. Hello out there. Hi, everybody. How's it going? Aaron from Solace here, back with you for yet another Solace office hours. It is November 21st, coming at you live from Singapore. It is 10 p.m. at night here. So we are across the globe, hopefully hitting most people during awake time hours, unless you live in New Zealand or Hawaii, maybe. I guess you might still be asleep. Anyway, thanks for joining, whether you're watching us on YouTube or on LinkedIn or on Solace Community, or if you're watching the replay later. I hope that you find this episode interesting. So I am very happy to introduce someone who's been away from my office hours for quite a while. My esteemed colleague, Tom. I'm going to add you back in here, Tom. Hey.
Hey. How's it going? I'm esteemed and distinguished. I'm doing really well here.
That's right. Mr. Distinguished Engineer. Anyway, hey, Tom. So, we've worked together for many, many years. And interestingly, when I moved to London many years ago, you were in Singapore. And now I'm in Singapore and you're back in London. So there you go. It's a full circle. So anyway, why don't you introduce yourself to those that don't know who you are?
Yeah, sure. Hi, everyone. I'm Tom Fairbairn. I'm one of Solace's distinguished engineers. So my job essentially is to explain Solace to people like yourselves, right? That's what I do. Been at Solace, over 10 years now. As Alan said, started off in Singapore in the tech support team over there. And then moved back to London and, moved into this more kind of SE customer-facing kind of role. So that's where I come from. Done a lot of work in finance, but also outside of finance. Part of that work in finance, funnily enough, ends up being low latency. If only that were relevant.
Yeah, so that's a nice segue there. So I mean, when I joined Solace, back Solace in the early days was very much focused on capital markets, financial trading platforms, our hardware appliance, very low latency, high throughput kind of use cases. And it still is. We're still very much deployed in a lot of these particular kind of these applications. And so a lot of our ongoing business, even new business, is coming from these kind of proofs that our hardware appliance is as fast and as good as what we say it is, right? So and as part of that, as SEs, Tom and I have both done a lot of proof of concepts. It's been a while since I've done it, but this office hours that we're doing today is basically a redo of a internal talk that I did about 5 years ago. And I thought, hey, this would be actually a great way to talk about Solace. Tom just did a low latency POC with not a customer, I guess, yet, a prospect. So it's all fresh in your mind. Now they're a customer now. All right. Yeah. Very, very good. I want to present low latency testing in Solace and how to do it. So if you're not in finance, and if you've never even thought of how to do latency testing, you're in for a treat. Maybe it's a bit technical, but I think it's a treat. Hopefully you find this interesting. So Tom, any words before we kind of kick this off here?
Just your point there about low latency is often in finance, right? Why is it in finance? Because generally, finance people can generally put a dollar number against a certain time of latency, right? 1 microsecond equals a certain number of dollars. Mm-hmm. But it does tie in quite nicely with the idea of a real-time event mesh, right? Yeah. The question there is about real-time, is what is real-time for you? So what's real-time for one person, right, is just not in the same world for another person, right? So if somebody's trying to react to eyeballs, then real time is kind of the 100 milliseconds. Yeah. Right. If somebody's tracking a vehicle, then real time is probably over a time span of seconds. Right. So it all depends what is real time for you. And something I think we're probably going to touch on later too is that we're going to talk about the broker here, right? Yeah. And the applications that are talking to the broker. Yeah. Generally, you're going to have a latency budget. So for your car example, when you're tracking a real-time car, it doesn't matter if your broker latency is microseconds if it's taking, 10 seconds to get across a mobile network, right? So
yeah. Networks become the dominating factor. Yeah, you have to look at each piece of it, right? So exactly. Anyway, so I'm in Singapore. Tom, you're in London, I'm assuming.
Correct. Yeah.
Where are everybody else joining us from? I always like to ask this. Most Solace people, when we do these live streams, kind of ask where people are joining from. So say hello, put it in the chat. Say hi. We're happy to have you here. Oh, we got a few comments actually already here. So hey, Nicholas, hello from New York. How's it going? Good to have you here. Who else we got? TK, how's it going? Hi, Tom and Aaron. Hello. And Himanshu, hello. Oh, you're in India today. Excellent. Well, that's great. Okay, so we got a couple people from APAC. We got a few from North America. Hopefully, a few Europeans tune into this as well. Not any bank holidays or anything, is it there,
Nope,
Tom?
not as,
All right.
not as far as I'm aware.
So let's share some slides here. So like I said, this is a deck that I presented internally. I modified it a little bit, but most of it's kind of left as it was. So hopefully this is all still fairly accurate. If anybody out there listening wants to correct me, again, throw it up in the chat. I'm happy to be corrected. Tom, you can keep me on track as well. Hello, Jim from Toronto. How's it going? Thanks for joining. Nick, Atlanta. Yes, good to have you. And oh, hey, we got Moatas from Ottawa. Hello. All right, good. We got quite a few people going on here. Okay, so Tom, yeah, let's. I got this table of contents here, and now, I mean, to be fair, Tom and I were talking about this earlier, so he knows what's going on, what we're doing. Let's have why latency testing? What is real time? Let's have a quick discussion about that. And this is kind of the agenda that we're going to be going into a little bit later. We'll define what latency kind of is, kind of how to measure it, why we want to be measuring it, how it's kind of measured in the Solace world when we as Solace technical people go to a prospect to do a proof of concept, and how we're measuring it, what we're looking for, how to tune your performance hosts, your typically Linux boxes that you're running these tests on, how to tune your Solace appliance, how to run your tests, and hopefully time for a quick demo, because we want to see this actually working. And we're going to use the London Performance Lab that Tom is instrumental in kind of maintaining there. So yeah, again, if you have any questions, comments, please put them in the chat. We're happy to answer them as we go. Let me just hide that. So why latency testing? I mean, Tom, yeah. So what is real time? You remind me of a funny story that I went to down to Italy for a prospect, and it was a truck manufacturer. And they were like, oh, we want real-time updates from the factory floor. I'm like, oh, that's great. We have this hardware appliance. It does blah, 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 microseconds, blah, blah, blah. And they were just looking for like an update every 10 minutes or so. That was real time to them. I'm like, wow, you probably don't need to be buying a hardware appliance. That's that level of real time is not. So yeah, how do you define real time? What are the requirements? Maybe you don't need to go as fast as what we're talking about. But a lot of the trading platforms that use our hardware technology, I mean, yeah, if you are just a tiny bit faster than the other guy at submitting that order, that trade, you'll make the money and the other guy won't. So I mean, it's always the trying to be fastest, right? So
yeah, and it's also worth pointing out, right? There are degrees to this, and you've got to cut your cloth to suit your budget, right? So some of these traders, here's a fascinating fact: air is faster than copper is faster than fiber, right? So they'll have microwave links. Because the speed of light in air is closer to speed of light in a vacuum than it is over copper, which is actually faster than fiber. Now, you plug into your broadband, which one are you going to say is faster?
Yeah.
That's when faster can mean latency, or it can mean throughput, right? Whereas we're talking about latency here, which is the end-to-end time it takes to get one thing. Yeah, exactly. Right.
This book, it starts off by digging that telco line between Chicago and New York just a little bit straighter to save a few milliseconds. It's amazing how latency you can really monetize it. So
But if you're in the line of building your own microwave link, to your colo, maybe this is not the discussion for you. You're probably, your budgets are probably a bit out of, kind of this discussion here, right? So there's a trade-off always, as there always is in engineering, between the utmost performance and everything else like cost, convenience, agility, and development, all that kind of thing, right?
And to be fair, like most of our kind of, our newer use cases that are kind of retail use cases or logistics or whatever, they don't need microseconds of latency. Milliseconds are definitely fast enough. So think of this as kind of maybe a bit niche, but also maybe just a little bit interesting. And it gives you an idea of kind of Solace's history and heritage, our DNA, and kind of, where we come from in terms of like high performance eventing, right? So Yeah, without further ado, let's get into it here, and let's kind of get through these slides here. We don't want to, take too long. So, what do we mean by latency? Now, for our purposes, we're just gonna define it as the amount of time it takes for data to move through a system, the system. Solace, an application on Solace. You can define latency probably other ways, but why are we interested in measuring it, right? Why should you care? Why should Solace people care? It's one of our main features of our hardware appliance. We're very fast, we're very low latency, high throughput as well. And the other thing is that we're very low jitter. The hardware appliance is kind of purpose-built, dedicated, hardware cards to do the messaging component. And because of that, what is jitter though? I mean, did I actually define it here?
Nope.
Yeah, I do a little bit lower down there. So jitter is essentially variation or variability in the amount of time it takes. So we're not just measuring how low your latency can go or what the average low latency is. It's also how tight your latency is, right? So it's one thing to have your average be, say, 50 milliseconds, but then if your 99th percentile was like 10 minutes, I mean, that's pretty bad, right? You want to have kind of your 99th, your 99.9th percentiles as close as possible, is reasonable to your kind of your average message, or your average latency. That's nice and tight. And part of the reason for that is because, I give an example there. A lot of trading platforms, you don't want jitter because it presents a chance to game the system. Like if you can happen to capitalize on one message where, it's an outlier and it's very slow, and you basically can maybe beat it to another exchange. I don't know. You want to minimize the amount of kind of intermittent delays or variability in your delays, right? So
yeah, one of my customers, they have built all their quant models, which they use to make these risk-based decisions. They actually build them at a certain percentile, right? So all of the other latency measurements don't matter. What matters is the latency at that percentile, because that's the only way the risk is going to align with what you're actually trading.
I think I understand that. Okay. Cool. What's your end-to-end latency budget, right? So, I mean, some of the customers we deal with, they're talking like, I want 50 microseconds, for like my entire, from beginning to end of my kind of application chain. I mean, that's ridiculously low. Maybe like a millisecond. If it's just like kind of how fast can you react something at a human speed, milliseconds are probably good enough, right? A couple seconds, maybe, if you're dealing with something that ticks along very slowly. Sometimes some of the things we're going to be investigating today really don't matter unless you're doing kind of like algorithmic, kind of ultra low latency type stuff. Oh, one other thing, I'd like to throw in here. Often just doing latency testing doesn't have to be for like hardcore performance. Oftentimes you might have a customer or using Solace with, for example, this happens a lot with our JMS API. You've plugged it into some kind of third party that uses the JMS API, like, I don't know, an integration platform, an iPaaS, or some kind of, ESB type thing. And they're complaining that it's running slow. They're like, my app XYZ JMS runs slow on Solace. You can be like, all right, well, let's hold on. Let's do a baseline with just the JMS API. So we're going to use SDK perf, which is our command line test tool, and just get a baseline in your environment, with the same network and the same broker and all the same setup. And just to get an idea of like, what is the Solace to network to broker component of that latency, and everything else after that would be added on by the application space, right? So it can prove or disprove whether it's the Solace that's being slow or whether it's the app maybe on top of the Solace that's being slow. So very, very useful for kind of, I don't know, pointing fingers at who's to blame about some things, right?
We call that diagnosing, not pointing fingers.
That's right. Diagnosing where the delay might be. So, okay. So how do we measure latency in Solace? Now we measure it from the publishing application when it hits send, when it publishes, sends a message through the API, through the network, into the Solace broker. Then it gets routed around to figure out who's it going to go to, back out the network, back to the receiving application, the consumer, and up to the API, essentially via a callback that it now can say, all right, I've received this message. So we're looking at from application send to application receive. We're not just looking at just the time inside the broker, right? We're not measuring kind of when the message enters the broker and leaves the broker. We're doing from app through the broker to app. So that gives us a more real world kind of usable time, right? And then everything after that you would add on, like your business logic would just add to that latency to some degree. It's very important to generally use the same performance host, to run your tests on the same host, mostly because of clock synchronization, especially at the rates that were, the microseconds kind of latency here. It would cost quite a lot of money to have a very in sync kind of timing setup between different hosts. So we almost always recommend that you run your performance test, your publisher and your subscriber on the same host, and ideally on the same CPU, or what do you call it, Tom? A slot, the same slot, right? Yeah, because if you're measuring clock ticks, different processors might be slightly different, and if your publisher and subscriber are on different slots, then you could end up some issues there. There are times when you need to be sending between two different hosts, like going across a WAN. You're doing some WAN performance testing, for example. And in that case, we generally recommend that you actually reflect the message back, the timing message back to the original publisher host, and just divide by 2. And that's how you kind of get your accurate timing there with kind of a long line. All right. So, and how do we measure these things? Well, so generally we are going to kind of, every time a message is received by the consumer, it's not going to calculate and do a whole bunch of stats immediately on that message. Because we're doing these latency tests, we need to be as very quick as possible when we receive that piece of data. We essentially just calculate the delta between the send and the receive timestamp and put it into a bucket. We have just a bunch of buckets. We're not keeping track of every individual message or time individually, because we could be selling millions and millions of messages. We just say, here's 1,000 buckets or 2,000 buckets, and we just put that measurement into one of those buckets, and we generate this kind of histogram, and then we can generate our percentiles from that as well, right? One thing about this, what do you think about this diagram here, Tom? If at first glance, what would you think? Is it good or is it not so good?
I'm hoping we can beat milliseconds worth of latency, right?
Yeah. Okay. Well, it's not even looking at. Okay. Don't ignore the timing. This is not Solace. I just grabbed this off of Google Images, by the way, everybody. This is not actually a Solace latency test here. I wanted to demonstrate the distribution of the data. So.
Yeah, that's key. That's why you measure 99.9th, right? So what's interesting about that graph is you've got an interesting peak up there.
Yep, this is nice. That's pretty good.
That long tail peak there, that's probably telling you about some systemic effect, right?
You could this guy, yeah.
So you could measure the time between the two, and that might give you clues as to what's going on. So could it be a TCP retransmit timer, for instance?
Yep. This stuff over here on the right, this long tail, these are all outliers. These are all kind of bad. This one spike here, that's what Tom's talking about. Yeah, that is particularly bad. You should probably go and investigate that. But ideally, what we want is everything's gonna be nice and tight, and we're not gonna have any outliers. That's our jitter, right? We want to keep that kind of to a minimum. So this is an example of a bad looking histogram, I would say. So. Now, some people might say, well, can't the appliance just measure this, right? Can't you just turn on a switch in the appliance and say, measure the latency? No, not really. It doesn't measure latency of messages going in and out. That said, there is, you can do a packet capture from within the broker. There's this kind of NAB PCAP utility, which is often used in troubleshooting issues. A solid support people might be asking you to run one of those. But it's not meant to be running, measuring latency. That's not what this is designed for. But something new. So this new, I added this just today. Distributed trace didn't exist 5 years ago when I first did this presentation. So could distributed trace help us with latency testing, Tom?
Yeah, I think so. It depends how you apply it, right? If you want to get the very lowest latency, the first thing is distributed trace is only going to help for guaranteed messaging.
Guaranteed messaging, right. So,
in the trading domain, that's orders and trades rather than market data. Right, but a lot of these trading platforms are going to be multi-geography. Mm-hmm. So, you might be trading in Singapore, but hedging against Tokyo, or you might be trading in New York and hedging against London. In which case, you're going to be having orders, trades, market data flowing between these two sites. Right? Once you get into that kind of across the network milliseconds of latency kind of thing, distributed trace will probably help you there, because it will, at the very least, it will draw the latency budget almost for you.
Yeah.
Right. So you can see an end-to-end latency plot.
If your appliances have very well kept in sync time clocks as well, that would probably be something that's required, right? Because if your clocks are out of sync, when it moves from one broker to the next, anyway, it could help. That's not distributed trace's main thing, you know. I mean, it's not for doing the latency testing, but it can possibly help you investigate some things, you know, for example. So yeah, maybe, I guess, partially is the right answer for that. Now, Solace internally, as part of various SolOS releases, does do these large kind of performance sweeps, both for throughput and for latency. Throughput with a large number of different message sizes, message rates, fan out, right? 1 to 1, 1 to 2, 1 to 10, and compiles this all into a big spreadsheet that is available internally to us technical people. And when we're working with a customer, we can provide, you know, for your specific use case, kind of what our best effort kind of lab results might be. So yeah, if you're very curious, you don't want to do all this testing yourself, you can ask Solace for some help and kind of guidance in terms of, you know, what is the best case scenario. But as always, it's always best to test in your environment with your particular network setup and your particular disk and everything, right? So
Nick Goodman's raised a good point here, is that, you know, the more useful measurement of latency is API to API, as we do, right? There's only so much use in measuring the latency across the broker, right? You want to know what the application to application latency is.
That's right.
There's another couple of quick points there. That is that if we measured the latency of every message going across the hardware appliance, we'd slow it down enormously. What's the point of that? Another point is that if you do need something that's going to sniff on the network and measure the precise latency of all this stuff, you can buy something like a Corville appliance or something like that, right? That is dedicated to doing that job, right? This is measuring latency is not our primary job. Our primary job is moving the stuff around so that it is low latency.
I mentioned that here. I forgot to say it, but yeah, there are like network tap type things that you can listen to, like the packets, and it'll do a packet capture like in real time on a 10 gig NIC for kind of analyzing that stuff. So sorry. Yeah. So I didn't actually see Nicholas's comment there until you were kind of halfway through there, Tom. So through broker latency is less useful than end-to-end since variability over the network. Yeah, obviously, hopefully you have a very well-tuned network. I mean, that's part of obviously the test setup, is you want to make sure that your ping times are all very, very consistent. Ideally, everything's hanging off the same switch. Anyway, I'm getting ahead of myself. We'll get into kind of some of the things that you will need to kind of be considerate of. All right, so let's talk about the different ways of measuring latency. There are different qualities of service, different delivery modes in Solace that we can use for doing this testing, and some special stuff, some IPC things that are not available in every API. But used to be five different types of messaging. Solace has now deprecated guaranteed cut-through messaging, so I've taken that out. I have kept the slide though at the end if you really want to see what cut-through persistence was about. But yeah, so let's do what most market data platforms, trading platforms are using. They're using direct messaging and how to measure that. So check out my sweet diagrams I got here. So here is my test host. I have my publisher and subscriber running on the same host. Here is my send and receive calls. Here's my API. This is the TCP stack within the actual host. Here's my network. And here is my HA set of hardware appliances with the NAB connected to the network, right? So typical standard setup for doing some performance testing. So what we are measuring in terms of latency is from the time the publishing application says send the message, goes into the API, which goes into the TCP stack, onto the network, through the network, through the switch. I guess I didn't try that, right? There'd be a switch here, and then into the NAB, which is the network acceleration blade of the appliance. Back out, it'll do a topic lookup, back out into the network, to the TCP, into the receiving API, and the on receive. So that is when we end the latency measurement, right? And that time is roughly 20 microseconds. Sometimes a bit faster. You can get it on some really good hardware. You can get it down to what, 18 or 17 maybe microseconds there, Tom. And this is average. We're talking average here. So that's just, if you're used to measuring things in milliseconds, you think milliseconds is low latency. Yeah, this is a couple orders of magnitude better than that. So about 20 mics. That's our direct messaging. This is our best effort. Best effort.
Best effort, yeah.
Yeah, at most once quality of service. Okay, so that's that. Guaranteed messaging, though. How about if you want to do persistent messaging? Well, because of the Solace Appliance's ADBs, the persistent memory card, it is still quite high performance. So what happens here is it's quite the same. A publisher app sends through the network into the NAB. The NAB will then, because it's a persistent message, needs to send this off to the ADB for storage. ADB is essentially a cache, a non-volatile cache. And because we have an HA setup, a high availability setup, that will get synchronously replicated to its mate. And only once the mate has acknowledged it, will it then send the message on. So it's a store and forward style of messaging, right? That's our typical guaranteed messaging. It has to be on both ADBs before it gets sent out to any eligible consumers, right? And it goes back through the network, back to the subscriber, and received there. So obviously going through these ADBs and going across to the ADB is going to add a little bit. How much does it add? Well, that's about 60 microseconds. And this is our fully guaranteed data path with the hardware appliances. So still quite fast, I would say. 60 mics. It's pretty good. This can fluctuate a little bit based on I don't know, things like the type of ADBs you have, the types of NABs you have. I mean, we're kind of talking, these are all kind of like top of the line type numbers here, right, Tom?
Yeah, of course, message size has an impact.
Message,
right?
Yeah, message
size. As does how busy things are, right? This is all happy path stuff here.
Happy path stuff, yeah, exactly. Yeah. And then the other two that are kind of more special use cases is our IPC capabilities. So this is only available in the C API, CCSMP, and our Java RTO API, which is a JNI wrapper around C. And with this special IPC library, so this is, by the way, this is not readily available. This is kind of something you have to license, I guess, from Solace, right, as an add-on. It allows you to either do inter-memory, shared memory communication between a publisher and subscriber on the same host, or you can do essentially a direct socket connection to a subscriber on a different host, essentially bypassing the appliance. So if if you have your publishers and subscribers set up in such a way that you're like, these guys are always going to be on the same host, you don't need to go through the broker. You don't need to go through the network to the broker. You can either do shared memory or TCP socket. And that's what we're going to look at first. This is the IPC over TCP. So same kind of thing. The publisher sends a message, goes into the network. Because it's a direct socket connection, it does not go into the broker, pops out here on host B. And because these are on different hosts, we have to do the reflect, right? We're going to reflect it back so that, unless these time signals are perfectly synced, you need to do a reflect. It's going to come back up to the application space, which then basically does that reflect. It publishes a response message back to the subscriber, and we measure this. And so this is going TCP through the network and back again, and that is about 12 microseconds of latency. So we definitely save some by not going through the broker. But if you because it's both ways, a 12 microsecond, divide that in half, and you're looking at 6 mics more or less from host A to host B in terms of the publisher to subscriber. Pretty fast, right? That's not bad. And this is, again, 10 gig network we're assuming here, and everything's kind of not being overloaded. The last one is our shared memory. This essentially, instead of when you connect to an IP address, instead of connecting to an IP address, you're connecting to, actually, I forget how the shared memory, there's a special kind of broker string you use, right? To indicate whether it's like a shared memory address.
Yeah, it's just a different connection string. So you just put SHM colon in front of it. And that's it. The API.
The APIs are the exact same, right? I mean, in terms of you write this application code, you're publishing, subscribing on topics and messages, and all you do is you're changing your connection string. and you can go from using a brokered connection to a direct TCP socket connection to a shared memory connection, and which really gives you the flexibility that you're like, all right, I always know that these publishers and subscribers are going to be on the same host. I can now, for latency reasons, I'm just going to use shared memory instead of the broker. Very easy to do. And you can mix and match. There's that IPC gateway where you can basically have some go inter-memory and some go to the broker, and yeah, all sorts of things. Anyway, this is the shared memory here. There's this little, basically you set up a queue or a buffer, kind of a chunk of RAM in between the different publishers and subscribers. And this, start to finish, is about 400 nanoseconds average for 4 and a bit. So really fast, really, really fast. It's probably not the fastest shared memory library out there. It's just the beauty that you can, basically, it's the same API as the messaging, through the broker code. Like, you don't have to change any code to make this work. You just change the connection string. So those are all the different ways of measuring latency in Solace. Typically, it's the first two. We're either doing direct messaging or guaranteed messaging, and it's kind of host, broker, back to the host. And today we're going to be mostly talking about direct messaging, because that's usually where people are kind of most concerned about their latency. So yeah, we're going to be aiming for that 20 microseconds of latency through the broker. As part of our demo, right? So yeah, let's see if we can hit that. So that covers the basics, kind of what is latency, how we're measuring it, how it's measured in Solace, and why kind of people care about it. How are we measuring it from API send to API receive after in between the broker, and which way we are measuring it. So now that that's all sorted out, let's get into actually how you get things set up, how you configure your stuff, and how to actually do the testing. So ta-da! Before you start, oh, right, yeah. Now, as when I presented this internally to Solace people, there are a number of internal resources that we have available to kind of learn and skill up on how to do this kind of stuff. Not all of it is available externally, but we do have a dedicated performance course. It's something kind of niche, that not everybody needs. But apparently, Tom, you were saying that you might actually have to be giving this course to some customer on how to do some of the very things we're talking about, right? So, yep. Learn a kind of, yeah. So, kind of deep dive on the TCP protocol and kind of everything there. Slow start and like all these like fast retransmits and how those impact your throughput. How to tune hosts, API threading and design, interrupting, like I don't know, all sorts of interesting stuff that you have to learn about, which you don't really have to think about unless you're going down to that level of really low level performance or low level latency, high performance, I guess. There's also this really good internal document that I like to kind of make sure that Solace people know about. It was written a long time ago and it's been updated throughout the years, called the Performance POC technical note. If you're a customer, if you're a user of Solace, talk to your local Solace SE and see if they can maybe get a copy of it. None of it's proprietary. It's just kind of really good ideas on how to kind of tune talks about networking, talks about how to tune your host. We're going to go cover some of that here today, but this is definitely the kind of the holy grail that I kind of based a lot of my knowledge on by reading this document a couple times to really kind of like for it to sink in, right? So I only have good things to say about it. All right, so a couple other things. Equipment is important. A couple times I've been asked to do a latency sensitive POC using like not very good, hosts. Like they had 2 cores. They were definitely not really very good machines. Don't do a performance POC on your laptop. Don't use localhost. I mean, don't run everything on the same host, for example. If you're really keen about proper latency, you want to make sure that you have proper performance hosts. You're going to tune them. You have a good network, because if you really care about, maybe you can't afford a 10 gig network. I don't know. Maybe, I don't have a 10 gig network around here. Maybe I just want to find out the best I can get. So, but there are things that you can do, like in terms of how to make sure your latency is going to be good. Cut through switches. I mean, yeah, again, if you want to kind of spend your money, buy some really good switches. What switches do you have in the London lab there, Tom? Do you know?
So the problem with 10 gig line rate cut through switches, all right? Because when I was buying them, that's what I thought. Oh, we might want to do latency testing at some point, so I'll get cut through switches.
Yeah.
And yeah, it works. It pays dividends.
Does it? Okay. Are they a lot more expensive than kind of regular, I guess, store and forward switches?
Yeah. So in a previous life, I was a switch designer, and designing cut-through switches is, it's quite difficult.
All right.
They're more expensive, and they're more valuable, right? So
yep. Well, look at it. Like you can shave off 3 microseconds for port-to-point latency. So I mean, again, when you're down into that kind of single, every microsecond counts. So solar flare NICs are quite popular in terms of high performance network cards. And there's something called onload or open onload, where you can actually use a CPU core that's you spin it at 100%, and it can actually be used to kind of bypass the Linux kernel. So take data directly from the NIC and stick it straight into your application. So you can actually shave a few more seconds off your latency if you want. But you burn a whole CPU core on that, right? So
in the interest of impartiality here, Mellanox do a similar card with a similar software stack.
Sure.
My latest experiments were with Intel cards. Got some quite good results with them too, right? So they attack this a bit differently. You've got different queues that you can steer towards different processes and things like that.
That's cool.
But yeah, consider your network card.
I would guess that there's quite a few things that are not on my slides here about like things that you can do to improve your performance, right? But these are some of the things that I ran into, and yeah, I'm sure there's quite a few others. So, and then some things about your network setup, like don't do your testing when you have like 5 or 10 network hops. Like, I mean, you're not going to get the best performance, the lowest latency that way. Ideally, everything's on the same subnet, on the same switch, so you're not hopping all over the place. If you're testing the best possible performance you can get, you want to kind of make sure that it's nice and kind of, as short a network hops as possible. Check your ping times, make sure they're not jumping all over the place. That's probably something pretty basic. Make sure they're nice and consistent, because obviously you want to be consistent. You want that jitter to be kept low. So just a couple of thoughts there, right?
Just on the network, network setup, clean networks, clean as in single hop, all that kind of thing, and clean as in not everybody else is talking on your network segment, because that will introduce jitter.
Right. Yeah. The busier your stuff is, that makes sense. All right. Okay. So so we've decided we're going to do a performance POC. Someone is interested in buying some Solace. They're going, all right, we want to do a performance proof of concept. I bought some servers. I've got some Solace hardware here. What do we need to do? Well, first thing we're going to do is tune our performance host. This is where our publisher and subscriber applications are going to run. And these are going to give us our baseline kind of best possible latency numbers. So how do we tune our host? Pretty much every manufacturer of high performance servers that I've seen has some latency tuning document that you quite easily find, So if you're running HP, if you're running Dell, whatever, any server of choice, you just Google, kind of latency tuning, and there'll probably be a document that shows you how to do it. Most of these assume that you're running Linux as your OS, because it is quite a bit more flexible in terms of its tuning. You can do latency tuning on Windows. I think it's just a lot harder. I've never had to do it, but I have looked at it and I thought, yep, this would be more difficult. So I'm happy I never had to do it. I don't know if you have, Tom, but almost everything I've ever seen, it's all Linux based. So yeah.
I've been asked to do some tests on Windows, and I basically said no thanks.
Nope.
Nope. Shut. I mean, as Aaron says,
no, that's
possible.
fine.
There is documentation out there, but it's nowhere near as refined as Linux is. Right?
Yeah, I just remember trying to do something where you like often you pin a process to a particular core in order to kind of make sure it's nice and isolated. I couldn't figure out how to do it in Windows. I would like run some SDK perfs and they'd be spread over all the cores. I'm like, I don't know how to control this. So yeah, from everything I've seen, doing this on Windows would be a lot harder than doing it on Linux. So hopefully you're going to be doing this on Linux out there. Generally, the performance guides, will offer somewhat similar advice. Obviously, some might be different, but generally it all says start off by going into BIOS. You got to do some tuning in there, disable things like energy saving, typically disable hyperthreading, sometimes disable turbo mode. I've seen other things where, it says enable turbo mode. Turbo mode is where it can change the clock speed kind of dynamically based on certain criteria. But yeah, go through your particular guide and read the steps on kind of what you should do. That's kind of BIOS. That's the first thing you got to kind of get set up. Any kind of energy saving. Then you're going to go into Linux. We got to do some Linux tuning. And the majority of the Linux tuning is going to be turning off any services that you don't need, right? Just kind of minimizing the amount of random stuff running on this perf host. And then moving around interrupts so as not to interfere with your testing. And interrupts, well, I don't know. Tom, you describe interrupts.
Want to describe interrupts or describe the tuning we're going to do with interrupts?
Well, just like what I mean, why are interrupts bad? I mean, that's kind of the why we're moving them.
The clue's in the name, right? So you've got some kind of asynchronous event, typically I/O going on, typically I/O from the network, and that's going to come along and it's going to want to run some code to deal with it, right? And what you don't want that to do is come in and interrupt your latency process, because that's going to, guess what, add latency and jitter, and you don't want that, right? Yeah. So, our typical recommendation is kind of up there in that the kind of core diagram up at the top. Is what we want to do is we want to move all of the OS interrupts, things like timers and things like that, onto one CPU. Yeah. Right, and that's going to deal with all your OS crap that's going on.
One core. Move it onto one core.
Sorry, one core. Yeah, what did I say?
You said CPU, but
yeah, one core. Good point. Yeah, you want to move that onto one core. And then typically, like, you're going to have a 10 gig NIC in there, right? And that's going to be doing interrupts because it's going to be receiving packets off the network and sending them to your subscriber. Now, you want them to be served quickly because that's in your latency path, right? So typically, you're going to allocate them to one core too. So far, we've already allocated 2 cores.
Yeah. Right? Put all that system background things that have to run. Like, you can't close down everything, right? There's definitely some stuff that still need to run. Put them on one core. Give your NIC its own core, and then ideally you should have the rest of the cores, in this little picture here, the core is kind of in the middle. These should be nice and clean from interrupts, from your NIC and from wherever else, so that you can run your tests and have nice low jitter. So here, we're not going to go through all the different, commands and all this stuff. I mean, you can Google this stuff. You can find it. If you're using Red Hat, there's this tuned ADM thing, which is very easy to kind of get set up. Tom, when you were doing some of this testing, you were finding that this SMP affinity stuff was not working as well as this could be out of date, this stuff here. So
I mean, I found it was all about tuned. Right, I actually wrote my own profile that combined some of the latency profile and network latency profile into one. All the instructions say echo something to proc IRQ, the IRQ number, SMP affinity. That gets overwritten, I was finding. So I think what I ended up doing, I can't remember what I was doing, something to do with ISOL CPUs and something to do with tuned. I can't remember, but yeah.
A couple other things I noticed. I mean, sometimes in your Linux settings, it can actually override your BIOS settings. It can actually cause your energy saving to kind of kick back in again. So there's things you can add to force your CPU C state. If you don't know what C states are, it's basically how much, how energy intensive, I guess, like how busy your CPUs can be.
Basically, it turns down the frequency and shuts off bits of the processor. There's 2 problems with that. If you're shutting bits of the processor and reducing the frequency, it's not going to process stuff as fast, obviously. But almost more importantly is that moving between these, say, C states takes a long time. It can take milliseconds, and that's going to clog your latency.
Yeah. So this basically just says run at full maximum performance all the time, never slow down, not the best for energy savings.
Yeah, I was just about to say, remember to revert this when you finish testing, right?
Yeah. And your fans are going to be going nuts and stuff anyway. So, all right, let's keep going here. So I don't have a picture of how it's supposed to be, but if you can, it's a bit small, but these are the Ethernet interrupts here. This is like ETH1, ETH2, ETH3. I have a couple NICs on here, and you can see these are all the different cores, and you can see that I'm definitely getting interrupts firing on kind of all of these different cores. So this is not a well-tuned system. Ideally, all of your Ethernet interrupts are all happening on one particular core. I wish I kind of got a screenshot when I had this tuned years ago, but if it looks like this is not good. This is basically catting proc/interrupts. So There are some tooling available to help kind of verify that your interrupt setting has all worked. There are some manufacturers that actually produce a tool to do kind of jitter testing. Solace has one internally called Idle Host Latency Interface Red Hat that was written by a former colleague of ours. And they all kind of operate in the same way. SDK Perf actually has this built in as well. There's a flag, I guess you call it, slash DKI. They all kind of operate the same way. Essentially, it spins a CPU. You peg it to one specific core using task set, for example, and you spin it as hard as you can. And you basically count how many clock ticks or how much delay was in between each loop. And if you don't have any interrupts firing randomly on that core, you should have basically very consistent, inter loop speeds. And you can kind of measure. You can see this little graph here. This is a dump from this Solace tool that we have. The difference between an untuned system, you can see quite a few loops maybe were between 5 and 10 microseconds, quite a few greater than 10 microseconds. And once you've tuned it and moved your interrupts around and you run it on a nice clean core, you should see something that looks a little bit more like this, right? Again, all going to reduce our jitter to make sure that our long tails, our 99.9 latencies are nice and tight there, right? All of this work, all of this tuning of the host, which can take hours, to get it, days maybe, to get it working, set up correctly, just to kind of get rid of some of these outlier type things, right? So quite a bit of effort, I think. One quote I'd like to throw out there to our colleague Dave McKay: not all cores are created equal. Some of them, even though it's the same chip and it's the same everything and it's tuned all the same way and all the interrupts are moved off, some are just jitterier than others. And the recommendation that I've heard from more experienced people is to pick the best one, the least jittery, and use that as your publisher. You want your publisher to be running on the most smooth because the publisher is inserting those timestamps in each message payload. So you want to pick your best core for your publisher. So anyway, so all of that is to get the your host set up and working correctly, right? Done. Okay, so we spent a couple days doing that. It's time to tune our appliance. You plug it into your data center, you cable it up, and we're done. That's it. It's tuned. We are tuned. We are tuned for throughput. We are tuned for latency. Part of the joy of the hardware appliance is just the fact that, it doesn't have an OS. It doesn't have a kernel. You don't need to move any interrupts around. It is all purpose-built, interrupt-free, ready to go. So yeah, it makes the hardware appliance quite easy to do testing with, isn't it, Tom? It's all the perf hosts that take the long time to get things running correctly.
Yeah.
The Solace software broker, the VMR that was released maybe 6-7 years ago. As far as I know, it's throughput optimized. It's not optimized to be really latency sensitive. There are obviously things you can do to make it go faster, to make it go better, and that's generally run it on a host with higher clock speed. The higher the clock speed, the faster the software broker will be. Better NIC, and of course a better disk. Right, running it with a spinning disk, you're not going to have quite as much performance as a nice SSD with lots of flash RAM cache in front of it. And if you're using Solace Cloud, or if your apps are running in the cloud, obviously you're going to kind of get what you get. Different cloud providers will have different qualities of service for their disk, for their compute, for their everything. And network latencies, who knows, right? I mean, if you're going across the WAN, that's probably going to become the dominating factor than the broker latency. The Solace broker might add, I don't know, ballpark it, maybe half a millisecond or something. It's not nearly as fast as the appliance, but it's not terribly slow. But going across the WAN could take tens of milliseconds or more. So, who knows?
I mean, all I would say is, if you are going to run the broker on the cloud and you need low latency, talk to your cloud vendor. So I have a customer that runs their trading platform on the cloud perfectly happily, low latency trading platform. The only way the project was successful, though, is when they started talking to their cloud vendor. The cloud vendor went, but we can do this and this and this. And it's like, well, that's not in your documentation. It's like, well, no, that's where you have SEs.
So we have some fancy things we can do, like on the cloud side, to make things go, okay, that's cool. And I know that Solace Cloud, I mean, we can offer recommendations on what we think the broker should be run with in terms of like the type of disk or the type of machine. I'm happy to provide that information. But yeah, your cloud vendor would probably have some even better, higher performance stuff. Maybe that. One thing to mention is the performance of your storage is going to be critical for your guaranteed messaging. Now, that's whether we're talking SANs with your hardware appliance, whether we're talking cloud disk, or which particular cloud provider. If you're doing guaranteed messaging, the performance of your disk is going to really come into impact your overall performance. Doesn't apply to direct messaging like we're going to do today, but yeah, something quite important there.
Quick one from
yeah,
Newton.
I see that. Let's bring that up here.
Yeah.
Cloud providers are known to dynamically change network and bandwidth on the fly on usage. Be sure to run latency tests for a long enough time to replicate steady state real world. Yes, we have this as a point later on, but thanks for bringing that up. That's a really good one.
There's another important point there too. The cloud providers, especially with the smaller machine types, often have burst credits that you can expire. So if you run it for a short time, you go, whoa, this is fantastic. And then you actually run it in the real world and 2 hours in, everything slows down. It happens.
It goes to a trickle and you're like, what the heck?
Oh, it drives you mad. It really does. Like, hold on, this worked 5 minutes ago. Yeah. Stuff.
Very good point. So yeah, run things for longer. Make sure that you don't have any caps on daily or hourly or whatever bandwidth or CPU or disk. I mean, the thing about the Solace broker is that it uses all of these things, and it uses compute probably less than your typical application would. It's going to be using network and disk primarily, and these are probably things that your cloud vendor is going to like to cap or kind of minimize. So definitely things to test for there. All right, so we're almost ready to run our tests. And then what time is it? It's coming up on the top of the hour. So this is going to work out quite nicely. I think we're coming close here. So now we talked about how we measure the latency, kind of from publisher to subscriber, but there are a couple different types of latency tests that we can run. Typically most people, when they talk kind of like the lowest latency number, this is kind of a 1 in, 1 out, publisher to subscriber, 1-to-1 kind of typical latency test. Usually these are done at message rates somewhere between, I don't know, I would say 5 to 10,000. It depends. If you're on the hardware, probably 10,000 to all the way up to 100,000. I mean, you could sometimes do millions of messages per second if you have multiple publishers. You need multi cores. But ideally that's somewhere in that sweet spot for message rate. Too fast, and you're overdriving probably the CPU on your perf host, right? That one core that's actually doing the publishing. You're not testing the broker's latency capabilities. You'd be testing your kind of the API's CPU utilization capabilities. And too slow, oftentimes people will run their latency tests. They'll publish at 10 messages per second, for example. And they're like, holy crap, the latency is terrible. What's going on? Oftentimes it's because, things like the CPU L1 cache might not be kept hot. And, kind of the CPU is unloading that piece of instruction and then reloading it back in. So again, when we're talking microseconds of latency here, you want to make sure that everything is tuned just right. So there are sweet spots to kind of measure that latency. Measuring under load. This is another thing where a lot of people that maybe don't really know how to do latency testing properly might kind of make some bad choices here in terms, they might just crank up the message rate on a single publisher, right? Just take a single publisher, run it as fast as it can. And they're like, I'm measuring the broker under load. You're like, not really. And you're not going to get accurate measurements because again, if your publisher that's doing the latency testing is like running at full speed, it's not going to be able to accurately inject those timestamps, and same with the consumer on the other side. So the way that you measure latency under load is to provide the broker with some background traffic. You want to load up the broker with, I don't know, what do you call it? A load generator, right, Tom? I mean, you run extra traffic through it, ideally on different hosts, right? Other hosts that are not your perf host that you're doing the testing on. And then you still run your latency measurement at that kind of sweet spot, 10 to 100,000 messages per second, depending on message size and whatever. And that is your actual kind of latency probe. So you're not, again, overloading the latency testing application as fast as it can go. You're loading up the broker with additional background traffic, so it has to deal with this stuff. and you're still measuring the latency of your app at reasonable kind of message rates. So, yeah, that's kind of.
I'd say that's the most common one that people are interested in, right? Latency under load. They want to know that they're not going to have jitter introduced just because, say, the market's busy or something like that.
Yeah, that's fair. So often in that performance spreadsheet that I was talking about earlier, you'll see kind of what is the latency at 100,000 messages per second going through the broker, 200, 500, a million, and you can see kind of like how that that curve might fluctuate. Obviously, it'll go up a tiny bit, a little bit, but it shouldn't go up a lot. It probably won't go down. I don't think latency goes down as a plan. Maybe it goes. Maybe at very low message rates. Anyway, and there's one other type of latency test that's quite complicated. I've kind of moved it to the outside the deck, but this is our first to last latency in a large fan out situation. So let's say you're fanning out, one message comes in to 100 consumers. What is the latency delta between kind of the first and the last? From my testing that I used to do, it usually looked like it was around the kind of the network serialization speed. So you kind of look at on a 10 gig network with a 100 byte message, blah, blah, blah. You can do some math. Solace randomizes the order of delivery, but because we use TCP, this is still like, kind of one by one, sending messages out the broker. So a bit more complicated to test. And again, probably only useful to a very small number of use cases that are comparing us to, I guess, to UDP would be the kind of comparison there, right, Tom?
Yeah, exactly. And it goes back again to that trade-off of how much money are you willing to spend for this? If you really are, if you've got an infinite bucket of gold, right, you probably go for UDP because you can afford to employ people to do nothing else but make sure your UDP network is well balanced and goes around stopping people plugging in the wrong connector into a UDP network, which can bring it down. You hear these stories from customers about, an engineer went onto the trading floor to diagnose something, plugged in their cable, which auto negotiated down to the wrong speed and caused a UDP multicast storm, right?
Yeah.
One of the advantages of TCP is you don't get any of that. It's much more simple and agile, but the cost is that you don't get the ultra low latency that you get with UDP. Right, got to stop us. We've got a question from Jonathan.
Yeah, we got a question here, and this is not a UDP comparison, but so Jonathan, if load testing across a WAN for real world application performance testing, let's say with 50 milliseconds of latency, all right, what parts of the test are serial, waiting on a response, and therefore limited to the 50 seconds, and what parts are parallel? How do we maximize parallelism with SDK perf to lessen the blow of the WAN latency?
There's a quote here that I was desperate to shoehorn into this, and that is, you can't break the laws of physics, Jim. I got it in, yes. Basically, look, if you've got 50 milliseconds of latency across the WAN, well, there's your latency budget is a minimum of 50 milliseconds. And okay, so you take 100 microseconds off with host tuning, well, you still get your 50 milliseconds of WAN latency, right? So,
I'll just mention all that host tuning doesn't actually really affect your average latency. It doesn't affect even your 50th percentile. It only affects I guess it would affect your average because like you're trimming down your those outliers, right? Your 50th percentile is not going to change at all when you do these kind of these host tunings. It's just going to tighten up that outlier budget. But yeah, all 100 mics even over versus 50 milliseconds, that's it's just going to be a tiny, I don't know, the amount that the Solace brokers and APIs add is minimal compared to 50 milliseconds of latency. But in terms of like what's parallel, I mean, obviously there's multiple messages in flight. We're not sending one message at a time, right? We're not sending one and then 50 milliseconds later sending the next one. These are streaming messages. So
we are using JMS. Sorry, just had to throw that in.
Oh, that's right. Yeah. If you're a JMS 1.1 publisher, then you are single round trip to the broker on each published message. So assuming not that, you are parallelized. You're parallelized in terms of, you are streaming your message data. Sorry, Tom, that's for guaranteed messaging, not for direct as well.
Yeah. Good point. I mean, I think what's important here, Jonathan, is that you're talking about parallelization and serialization. Remember, this is latency. So it's the end-to-end time for one thing. Like it's a bit like the big fat pipe problem, right? You've got this massive pipe and you pour some water in it's still going to take the same time for that water
Still
to get
long.
from one end of that pipe to the other. The fact
Yeah.
that you can fit, 100 gallons of water in that pipe at any one time and move that 100 gallons of water from one end to the other much quicker than you would, say, with a smaller pipe, that doesn't affect the time it takes to get one piece of water, one molecule of water from one end of the pipe to the other. And that's what latency is. And that's why when you talk about fast, what do you actually mean? Do you mean how fast can I get a gallon of water through the pipe, or how fast can that one piece of water get from one end of the pipe to the other? This is latency.
Throughput
It's how long it takes to get throughput versus latency. This is how long it takes to get anything from one end all the way to the way to the other.
Yep. Good question though. It's definitely interesting to think about. I want to, in the interest of time, Tom, we're at the 1 hour mark. I want to make sure that we get our bit of testing done here. So this is going to take a few more minutes. I got a couple more slides. I will provide, maybe I should put these slides on Solace Community. I will put these slides on Solace Community for people that want to learn a little bit more about it. There are, in SDK perf is the test tool that we're going to use. This is available on solace.com/downloads, or if you're a Solace customer, inside the products file drop SFTP server. SDK perf is available for Java, C, .NET, but C and Java are probably the APIs that most people use for testing, or JMS. And there are these command lines, all starting with -L, for doing these various latency things. So we can specify how many buckets are in our histogram, the size of each bucket, which is this granularity factor, the precision in terms of like how many decimals we have, a warm-up, which you need. For Java applications, they need a warm-up. Quite a bit of detail here. Again, we're not going to go into it in fully because we're running out of time, but we are going to show you. But just as an example, I got this one slide first. I forgot. C is going to give you the lowest, fastest, most consistent latency out of all of our APIs, right? It always has. So if you want like the best possible, you can run the C API, CCSMP. Unless you're using some high-end JVM like Azul Zing or something that kind of minimizes its garbage collection, Java is always going to give you worse outliers, I guess, shall we say, right? Because garbage collection inside the VM is going to kick off every once in a while. It's a bit non-deterministic. And it's going to screw up your latency outliers. So while your average latency or your 50th percentile might be almost identical to C, those 99th and 99 plus percentiles are going to be a little bit quite a bit worse.
Yeah, don't forget with Java, you've got the bytecode interpretation to do too. So it's not just the garbage collection; it's also the hotspot stuff, right?
Yeah. And in terms of hotspot optimization, I mean, with the C API, you can basically start doing latency tests almost as soon as you start up, right? Give it a 1 second warm up to kind of warm up the network, the TCP connection, and just make sure it's all running before you start doing your latency testing. In Java, you can provide a warm up, sometimes 30 seconds, sometimes a minute or two, to get really nice, consistent latency numbers. Something to consider when you're kind of doing your Java testing. Don't start taking measurements as soon as you start the app, because you're going to get some pretty terrible kind of outliers at the beginning before it kind of optimizes. One thing I just kind of want to note, again, I have another slide on this later on in the appendix, but LG is the bucket size, and you need to play with that when you're changing from like regular LAN testing to WAN testing, or you're changing APIs. The default value is well chosen for LAN testing, but you might need to mess with this a little bit, and it's a bit confusing. So we'll put it in later. So these are some of the tests that Tom is going to run. He's going to demonstrate us some SDK perf running in the London lab, essentially which IP to connect to, a username and password to a particular broker, a topic. Obviously, we're going to be publishing on direct messaging topics. So a publish, a subscribe, and a publish here. The fact that we're doing -L or -LAT for latency measurements. Here is this warm-up of 1 second, and I'm using 4,000 buckets. This is not the exact same command that Tom's going to use. On the publisher side, you can see that I'm publishing at 10,000 messages a second with 100 bytes. And I've added that because I'm doing 1 second of warm-up, I've added an extra 10,000 messages to my publisher. So now this PSM thing is quite important, I guess, Tom? This is the switch publish publish smooth. Is that the actual name of
Yeah,
it?
publish
Yeah.
smooth. Yeah.
And it basically helps make sure that your application, your timestamps are nice and, I guess, consistent. I guess it's a busy wait between each message rather than a thread.sleep, which can introduce interrupts and context switching, right? So
Yeah, as you say, you want to keep that CPU spinning 100% hot, right? That's how you get low latency. Yeah, that's what the PSM switch does. Yep.
Yeah. And then when you're done, when the publisher is done, hit Control C on the subscriber, and it's going to dump out its stats. So you can see here, it kind of tells you what the latency warmup was, how many messages it received, and it gives you these latencies over here. So what's the minimum, the average, the max, what the percentiles are. Now you might see something that looks more like this: cannot complete these percentiles, blah, 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 not enough latency buckets. This is usually means you don't have the correct bucket size or the correct number of buckets chosen for your particular use case. Again, if you're publishing over the WAN, I can show you running a Solace Cloud. I really had to adjust my buckets to be quite a bit larger because we're talking, milliseconds and not microseconds. So I had to make my buckets quite a bit bigger in order to have enough buckets that I could calculate these additional percentiles. So if you see this, not enough buckets, you probably have to play with or increase your bucket size. So actually, let's just get straight into it. And Tom, show us how to do this demo. Oh, you're gonna have to share your screen here.
Yep.
So Tom is going to be running this in the London lab with a hardware appliance and a Linux host.
Yep.
And I don't know how tuned this host is, Tom. Is it well tuned or kind of tuned?
Why don't we see?
All right.
Okay. So, oops, that's the wrong one. Hold on a minute. Sorry.
That's all right.
Let me just share the right one. I might have to just share my whole screen instead, but that one.
While you're doing that, I'm just going to say, Jonathan was saying asking how to maximize throughput, not how to minimize latency. Yeah, there are, I guess, 50 milliseconds. You can do things around TCP window size, and maybe if you're doing guaranteed messaging, you want to make sure your AD window is quite large enough that you're not blocking ever waiting to send messages down that pipe. But I don't think there's much you can do. I mean, we're going to maximize a TCP link as much as possible. I guess, yeah, 50 milliseconds that's not huge, Tom? I mean, you wouldn't need to parallelize like multiple TCP connections or anything like that at that point. So
depends what you're doing. Depends what that's your round trip time. What's the bandwidth? All that kind of thing. There's a lot of
yeah,
a lot of stuff there, right? But I think Jonathan said I was thinking of throughput rather than latency. So yeah.
Mm-hmm.
Yep.
All right, so I'm going to add you to the stage here. Let's take a look at Tom's laptop, or not laptop, perf host.
Can you see my screen here?
Yeah, do you want to zoom in like a click or two maybe?
Okay. How's that?
All right, that's good. So we got, so on the left, we got, what do we have?
Yeah, so first of all, task set minus C1. I'm pinning this to core 1, right? Remember, we had one core doing everything else, one core doing the interrupts from the network card, and then 2 cores in the middle. In this particular case, it's a 4-core host.
So I'm gonna have it's only 4 cores.
Yeah. So I'm going to have 2 cores in the middle. So that's core 0 is doing the OS. Core 3 is doing the network card interrupts. We're going to have cores 1 and 2 doing the actual application stuff, the good stuff, right? So that's task set minus C1. SDK perf C, because SDK perf C is always going to give us the best results. And then I'm going to connect to this host. This is an appliance, the NAB. Right, not the management port. You can try that if you want, but you won't get very far. Just authenticating. I'm going to use a nice small topic, and there's one thing I've forgotten. I'm going to specify a message size. Oh no, that's the wrong window, isn't it? So this is just the subscriber, and then turning on lat L, whatever you want to do. So the way I'm
and your warm up, I think you deleted the warm up there. So
this is SDK-PFC. It's using
a default of a half second. That's a good number.
Let's put one in just for the sake of it. Let's take 2 seconds.
Sure.
Yeah? Right.
All right.
So this is our subscriber, and we want this running first. All right.
Yep.
We don't want to be publishing messages that we're going to ignore. So away we go. We set our CPU mask, and we're running away. Okay. Publisher. task set to core 2. Great stuff. Okay,
Yep.
do the same thing. Here's my publisher topic.
So they're each pinned to their own core, so they're not going to interfere with each other. They're each going to be about as accurate as we can have.
Yep. And it looks like I've got some noise in there. That should be like that. So I'm going to send 25,000 messages a second because that's a good number. I'm going to set my message size. So let's say 100 bytes like you did. Notice I've got PSM, publish smooth. Right?
Publish
so
smooth.
Spin the publishing core as hard as I can.
Busy wait.
Right? Busy wait, indeed. Yep. All right.
Do it. And these are 100-byte messages, everybody, so which is fairly common for our direct message testing. I mean, that's probably the go-to message size.
Yeah, I mean, market data messages tend to be small, right? You're not sending the whole book, you're sending an update, right? First example of event-driven. Yeah, so it's going to take a while to run. That should be 30 seconds, I think.
30 seconds? Oh, no, that was way less than 30 seconds.
Right, good. It published at 25,000 messages a second. We published our 500,000 there. All right, so let's
20 seconds there.
Hit Control-C. That stops our subscriber running.
Pretty impressive. Yeah.
And we're going to print out some numbers, right? So, yeah, you know, average of 18, 99.9 of 19. I'll take that. That's nice narrow peak, right? That's what we're looking for with low jitter.
That is,
6 of standard deviation there. Can run a quick experiment we did earlier. We're going to do two things. First of all, we're going to unpin the cores.
All right. Let them run wherever they want. Yep.
Yeah. Let them run wild. And we'll increase the precision. So that's... oh, no, I don't need it there, do I? I need it over here. So I'm going to use that latency precision option.
Oh, yeah, because like we don't have any decimal places there on the you can't see it. Yeah, 19 point what? 19 point... yeah, that'll help a little bit, I guess. So we've
talking amongst yourselves while the tension builds.
So we still have the publish smooth turned on. So we're still doing a busy sleep or a busy wait. Sorry, but yeah, these are we haven't pegged it to a particular core, so we're letting Linux kind of run this wherever it wants. Maybe it'll be okay. Maybe it'll be a bit. It's probably going to be worse. I'm assuming.
Oh, there you go. It's almost identical.
Not too bad. Not too bad. All right. That's
so that shows you that actually the Linux scheduler is pretty good.
Sometimes.
Sometimes. Now, we've got lucky here because we've pinned stuff. What's probably happening is the scheduler is saying, "Oh, well, core 0 is pretty busy. I'm not going to put."
Turn off that the publish smooth, and I bet you it's going to go
a
bit worse. So,
yeah.
So because it's the publisher is doing a busy wait, Linux is probably not context switching or interrupting the publisher because it's just literally spinning as fast as it can. Getting rid of publish smooth, it'll do a thread sleep and allow it to be context switched out whenever Linux might want it to. So I'm guessing there's going to be quite a bit worse latencies now here on this run, as a guess. Any guess? We should have people guessing online. All right, let's see here.
Look at that. See?
Yeah. Not terrible though. I mean, but it did add about eight mics or so. Yeah.
Yep. There's another experiment we can do here, just quickly. So what I'm going to do is go back to our original.
Yeah.
There's our latency warm-up 2. I'm going to use a different host. I'm going to use a different appliance.
Different appliance. Okay.
Oops, not that one. Sorry. So I'll use a different.
Latency at office. Oh, you made an office hours VPN, eh? Nice.
I did.
Oh, wow.
Get me.
Feels special.
Right, here we go.
Yep. All right. So this is you're pinning it back to a core, and it's the original setup. You're just changing which appliance you're connecting to.
Exactly. Right.
Okay.
So, all right. Quick question for you then, Aaron.
Yep.
Would you expect going to a different appliance would make a difference?
If it's in the same place, I think it should be the same, right? I mean, that's the thing about appliances. They're very deterministic in terms of their performance. So if it's a 3560 and with the same NIC, then same NAB, then yeah.
Exactly. Right. So they come pre-tuned. So it's not like there's going to be any tuning going on.
Yep.
So really, we should expect to see things identical.
Yep. Fairly like for like.
Not really.
That's not quite as good.
Yeah, it's not quite as good. Now, I happen to know, because, we'll put the network together in the lab, that actually if I go to this 150 address, that appliance is sitting in a different cabinet. So these messages are having to, these network TCP frames are having to go down to one switch. That switch is then picking the next switch across the trunk port to the other switch and then up to that appliance.
All right.
So
we're getting added latency latency. Yeah.
Yeah. So actually, it's surprisingly small. It's only a couple of microseconds.
Yep. About 2 microseconds or so. Yeah.
Yeah, it does help to illustrate that even in a super well-contained, well-constrained, well-built network, right? Your network topology is still important. Still going to make a difference.
You should have had the extra precision on there to see some decimal points there, but as a counter to your nice 10 gig lab setup, I actually, just before we started, I kind of whipped up a broker running. Well, I'm using my partition queue demo broker that I have kind of lying around, and an EC2 instance running in the same data center. It's AWS in Singapore, and I did a quick latency test just to see kind of the comparison between these nice numbers that you're getting in the dozens of microseconds and what you might expect if you're running in the cloud. So let's see. Okay, let's take a look here. Oh, that's not bad. I mean, that one extra hop. Well, I guess 2 because it needs to go both ways, but that's not too bad. You want to see what it looks like on my side on the cloud?
Let me stop sharing.
Yeah,
let's see.
Oh man, I don't think you're gonna be impressed, but let's just say that. So,
it's worth. Let's quickly point out that we're running on the software broker here. So this is not a hardware appliance running in the cloud. It is the software broker, right?
Software broker. This is Solace Cloud Dev Instance. So only 2 cores. Probably not the best networking that you can buy in the cloud. Probably not the best disk. It's direct only. I'm using Java SDK perf JCSMP. So again, not C API. So this is definitely on the lower end of the performance kind of spectrum. You can see here where I've modified that granularity factor. The default in Java is 0. I've made it 6, which is 2 to the 6 bigger bucket sizes. So let's start up, and I'm going to do a 20 millisecond warm up or a 20-second warm up there. Let's get that going. Oh, he's going to be echoing the message rates to the console because I forgot to turn that off. Let's do, I'm going to do 5,000 messages a second, not as nearly as fast as your 25,000 messages a second there, Tom? Yeah. So I'm going to do this. We're going to do 5,000 messages a second. And I think it's a 20-second warm-up and then 20 seconds of measurement, latency measurements. Again, when I was doing my real Java testing for this latency POC way back in the day, I think I did 2 minutes of warm-up and then 30 seconds of testing to get kind of nice numbers. And I found that at least 2 minutes of warm-up was kind of really required to get nice, fairly tight kind of outliers with your...
Typically when you're measuring real-world scenarios, you'll have quite a long time period, right? So something like 10 minutes or something like that, because the whole point with latency is it only takes one little thing to come along and interrupt things.
There we go.
Goes out the window.
So watch check this out here. Boom. Look at that.
Hey.
Yep. So my 50th percentile is 1.1 milliseconds. So Tom, you were measuring things in tens of microseconds. My 99.9 is 25 milliseconds. So completely untuned. I don't know what core this is running on. I haven't tuned my Solace, my cloud broker. I have no control over. I have no control over the how far these are in the data center, what the networking path is. So obviously a lot more difficult to get nice tight numbers using stuff in the cloud, right? Just as a counter, I guess, to your nicely tuned environment there. So
a quick point on those statistics. Note that the average is bigger than the 50th percentile. Right. Well, how can that happen? Well, what that's telling you is there's a big long tail, right?
Yeah. This is the mean. This is mean.
Yeah. There's a whole bunch of big numbers, big latency numbers that are dragging that mean right up. Right?
That's right. Now, you might not want to use SDK perf, like, I mean, there are times when you want to use your own app. I've had customers say, hey, I've written this Java app. I'm getting pretty bad latency. Why is it so bad? There are some things that I've seen that are pretty silly, things to kind of keep in mind. Things, again, maybe you just aren't aware of if you've never kind of done really hardcore high performance latency testing at the microsecond kind of level. I've seen people try to like print out on the console each individual message that they've received. Anything where you're doing IO, especially to the console, is just going to slow it down way too much. So like basically the only thing, SDK perf, it literally, all it's doing is it's just before it sends a message, it's sticking. Actually, wait, Tom, you sent me a picture. Did I put it here? Yeah. Oh, I did. Awesome. Yeah. So literally SDK perf is just before it sends a message, it grabs the timestamp, sticks as the payload, sends. And that's it. It's just really basically just you're setting the timestamp just before you send the message. And then it goes into the API, and then it goes into the TCP, and then it goes through the network to the appliance. This appliance has two NICs, Tom.
That's
the same NIC, I guess. It's popping back out, and then comes into the receiving application, the consumer here, and basically in the callback, pop out that timestamp, and don't do any stats. Don't print it to the console. Literally just take the delta from current to my the timestamp in the message, and store that in a bucket. Say, what's this delta? Stick it in a bucket. Next. You want to make sure that your callback is exceptionally fast. That's the main thing, right?
That's just generally good practice anyway.
Be fast in your callback is generally good. Yeah.
Don't mess around in your callback.
That's right.
We've got Ken Barr's voice in my ear going, don't block the callback. Don't block the callback. Right.
Yep. It's not as important. JCSMP, it's a little more forgiving, but in C and .NET, you definitely have to be quick. If you ever want to use some Java RTO, I've written some test examples on how to do IPC testing. But to give you an idea, like if you're a Java person, you want to see some reasonably good performance latency testing, you can check this out. There are a few differences between C and Java. Again, we're not going to go into all the details, but a couple ones that you might want to be aware of. In C, there's only one thread between reading from the socket and dispatching to the application, which is why Tom is just saying don't block up the callback, because it's the API thread that listens to the socket and does timers and other things. In JCSMP, there's actually two threads, so you can be a little bit more forgiving. There is a session property called dispatch on reactor to get that C-like behavior with only one thread. All of our various wrapper APIs that wrap around kind of either the core JCSMP or core C APIs are going to be a little bit slower. So whether you're using .NET, that's a wrapper around C, JMS, which is a wrapper around Java, the new Java API, which is a wrapper around JCSMP, for example. These are all the C API and the JCSMP API are your kind of lowest level APIs that we have, right? That are going to give the best performance there. Guaranteed messaging persistence and throughput. Yeah, we have AD window size and RTT are kind of going to determine some things. So I think that's about it. Oh, we have a few things on troubleshooting. As mentioned by Nicholas and Tom there, cloud bursting might be an issue that you're running into. Like if you have good performance for a bit and then all of a sudden it goes to heck, you might want to check to make sure that you're not running out of credits or something for that particular hour. Generally, if you're not getting good results, you're probably either hitting a CPU bottleneck or a networking bandwidth bottleneck. There are things you can check in the broker. There are stats. Because the Solace appliance implements the TCP stack itself, you can see on a connection by connection basis what the TCP, the retransmits, the fast retransmits. If you have any out of orders, you can check to make sure that the stats are clean, either in the event log after the client has disconnected or in CLI doing show client connections wide.
Yeah.
You can see TCP stats in there.
If you see any retransmits, like fast retransmits or timed retransmits, it's you need to look at something else.
You're overdriving the network. Something is,
or CPUs in the receiving host is unable to keep up with it or whatever.
That's right. And making sure your hosts are really tuned. Like, have you actually tuned it properly? Maybe you rebooted it and you lost all your tuning, right, Tom? Sometimes that happens.
I can't imagine that happening. Yeah.
And you have to like rebalance all your IRQs. So things to double check. Check your CPU jitter. SDK perf can print some helpful stuff if you do -D. And of course, come find us on Solace Community or ask your friendly local SE if you can help with doing some of this latency testing. So. That's some troubleshooting. I think, is that my last slide? Oh, it's our little wrap up here, right? So, we talked a lot about the hardware appliance because most of our customers who are want really, really low latency are going to be using the hardware appliance. That's what it's good at. And that's what it's, going really fast, high throughput, low average latency is good, but also being very consistent. That jitter, keeping that nice and tight, that's also very important. And it's tough to be good at both, right? It's easier to be, I don't know, just good at one. I don't know if it's easier. Can you be low jitter but like terrible latency? I guess you could be like, we have the tightest jitter, but it's 1 second.
It's quite easy to do. If you get stuff early, just delay it.
Just delay it. Yeah, we're very consistent. Slow.
Yeah, we're consistently rubbish.
Yeah. And of course, we could have a little discussion, talk off on about trade-offs here, like UDP, like that fan out use case, right? So that's one thing that where Solace is maybe compared to, like, if it's a large fan out situation, maybe you want to use UDP. It's going to give you the most, I guess, consistent latency in that kind of one-to-many kind of style of broadcast. But using TCP has a lot of advantages, right? It's per connection isolation. You can do more slow consumer isolation. You can. There's built into the network layer. There's retransmits and rebroadcasts out of orders, resynchronizing. If you lose a packet, it deals with
the WAN a lot better than UDP. It deals with cloud a lot better than UDP.
That's right.
UDP is possible in the cloud, but good luck, my friend. It's not easy. UDP basically, super low latency will cost you a lot.
Yeah. It's complex, but I don't know. That's a discussion for Solace Community. Yeah, come find us on Solace Community. Call us out on anything that we said here today. We're happy to discuss this in more detail. That's the end of the presentation. Oh yes, hashtag Solace rules. a bit biased there. I think I forgot to take that out from our internal presentation. So that's the end of this. That's the end of this deck. I was going to say if there's any questions out there, but people have been asking questions. And of course, if you have more questions, solace.community is the place to come and ask them. People like Tom and I and lots of our other SEs hang out there, SEs, PSGs, and developer advocates. We hang out there too. So, and we're happy to talk about these kind of things. So, Tom, great to have you. We're way over. It's an hour and a half here. I was pretty sure that we're not going to be able to cover everything in an hour. And, we actually chopped stuff out of that deck. We could have gone for a little bit longer, but until you really start to do this stuff yourself, until you kind of really, I want to do some really proper latency testing, you don't maybe realize exactly how complicated and fiddly and twitchy it can be, right? It's I
call latency testing the great humbler, because you can have brilliant reasoning as to why something should work, and then you try it and it does the opposite of what you think. Basically, it's the tests that prove the point, right? It doesn't matter what you think. The test is the important thing of what it tells you.
And things like different cores give you different amounts of jitter. It's just sometimes it just drives me nuts, and I'm like, why is that? And the same server with the same chip and everything will have different jitter profiles on different cores, And so I know that on this host I have to use this core for the publisher because that's the best one. And I'm like, why? I don't know. It's strange. It's finicky, right? So
question from Jackson.
Oh, there's a question. All right, let me check it out here. Just before one thrown in just before we go, Jackson Ho, hello. How do we find ideal bucket size value for? That's a bit tough. So, trial and error.
I was just going to say exactly that. Basically,
trial and error. Really. I have actually a post on Solace Community. Let's see if I can find it really fast.
So a good way, Jackson, is
you talk, Tom. Yeah,
you'll get a maximum number from SDK Perfect. So the maximum latency was this. So you want to tune your bucket size for that maximum latency. Right now, How do you tune your bucket sizes? Well, that latency granularity factor that Aaron was talking about, it depends on which version of SDK, which library version you use. But once you know that, there's a little bit of maths you can do, like is it some power of 2 of the clock cycles or something like that. There we go, and there's the discussion.
Yeah. So, oh yeah, it's sharing the right screen. Oh, good. You can see what I'm doing anyway. Yeah, so this is kind of, I go into talking about the bucket size, and yeah, you basically kind of figure out what the max bucket size is. I talk about how in C and Java they're measured differently, which is really confusing to a lot of people. But basically every factor you go up, like from 1 to 2 or 2 to 3, you're doubling. It's 2 to the power of that. And so in Solace, you're measuring it in clock ticks, or sorry, in C, you're measuring it in clock ticks. In Java, you're measuring it in microseconds. And you basically say, what's the maximum? And then you figure out, okay, if I have 1,000 buckets, I need them to be at least this long so that 1,000 is at least covering that, that max, right? So yeah, a little bit of trial and error, I think, is how is the professional opinion and way of doing it. So
yeah.
Maybe we should make a little helper script that it's like, all right, run this command, and then it will tell you if what to make LG and LB for the ideal setup. So that might be what we do. Oh, weird! It shows up as Aaron, and this one shows up as Solace.
There you go.
Did I post it twice?
Yeah.
I don't know what's going. Anyway, thanks, Jackson, for the question there just before we wrapped up. Again, if anybody else has more questions, come find us on Solace Community. Post it on this thread that I just pointed out here. Tom, it's been great to have you, man. It's been a long time since we've done an office hours together. You were definitely one of the originals when I first started doing these way back when. But yeah, it's been at least a year, probably longer, maybe 2.
Yep.
I think the last time you were doing it, you were wearing your kids giant game.
Yeah, that's right. I remember that. I had short hair then. So.
Yeah. Any last word before we wrap up here?
I don't think so. I mean, one thing you can say is with your Solace hardware appliances, you get a really good combination of low latency, not ultra low latency, but claim to be ultra low latency. But you get a great combination of low latency with simplicity and performance. Right, yeah. It's a really nice sweet spot, and basically, I dare you to try and find a lower latency TCP broker. Right, it's basically the best piece of TCP technology you can get in this part of the tech space. Right?
And due to its awesome performance, even though the cost per unit box is high, the cost per message is actually very low. It actually is. You get a lot of density, in terms of your performance for that as well. Massively. So, hundreds of thousands of guaranteed messages a second and millions of direct messages per second is pretty impressive. Anyway, thanks everybody. Thanks for tuning in. I hope for those who stuck around for the whole thing. Yeah, it's an hour and a half here. Gosh, it's 11:30 at night here in Singapore. I'm gonna head home soon, I think. There, Tom. Thanks a lot for doing this with me. It's been great.
Thanks. Enjoyed it.
Yeah, good. Thanks everybody for watching. And if you had questions answered, I'm happy. I hope that it worked out. But come find us on the community and ask some more. All right. Okay. Thanks, Tom. See you later, everybody. I'll see you next, hopefully just before Christmas for maybe a quick little special. Man, I got something special planned. We'll see. I'll see you next month. All right. Bye-bye.
Bye.